very quickly just going to mention EEG. Might do something like that next time. EEG is used in the medical world. This is electrodes on the outside of the head for analysis of which regions of the brain are active at different times for people with epilepsy. So it is used in the medical world to some extent. More likely you're going to see either fun uses of it. This is as much, I think, for the visual effect as anything else. But it's electrodes. The particular research is looking at which regions of the brain are active when the person's listening to different pieces of music. This one is the more typical thing you'll see. Some 29, 30 electrodes positioned at particular points on the outside of the brain. There may even be something in here with people. Is there? Yeah. And the person is learning to think in a certain way that drives a little robot buggy around. That's each of the electrodes is picking up on 20, 30 million, maybe more neurons. So there's a lot of signal processing involved to get the intent out of it. And you can get good results with the robot body. 8, 9 times out of 10 the buggy goes in the right direction, which is very good. But for something like a fail-safe method, I mean, it might even be useful for steering a boat, or where if you get it wrong you can re-steer. But driving a car around the centre of Prague would be a little bit dangerous. 9 times out of 10 it goes the direction you want. 1 out of 10 it doesn't. A little bit dangerous. So I'm not going to say anything more. Much more interesting for me, cochlear implants, spelt either E-A-R or E-A, as we'll see. So I'll put both those in just to mix it up. Again, more neurally based. And the basics, a lot of hearing aids now, rather than the standard more mechanical route, the electrical route, different versions are all referred to as cochlear implants, whether they're stimulating the cochlea or not. Specifically interested in the cochlear versions of those, but we'll see, there are different ones. So, signals from a microphone transmitted to electrodes that are implanted in the cochlea into the auditory nerve can use, to some extent, digital signal processing techniques from the microphone to either amplify or particular frequencies or to extract certain features. Those people that are fitted with them, and they're getting better all the time, now it's looking at, there's well over 100,000 people around the world, so large numbers of people have cochlear implants. And the person, certainly speech is obviously one of the things. They would typically still perhaps use lip reading to help, probably because they have learned to lip read to a certain extent, because they've lost hearing and so on. But they can recognise speech usually. We'll have a nice little clip, which hopefully I can get the audio out to you. It'll probably ruin your recording altogether, but we don't have any audio output here, so you're going to have to listen carefully to what comes out of my laptop. The person would tend to prefer no visible signs of an implant. They want to appear pretty normal. And that, because of our ears, that's quite useful because you can hide pieces, if it's external, you can hide pieces of technology behind the ear, maybe in the ear to a certain extent, but behind the ear. So power packs can be external without a visible sign to the front. So ears are with visual neuroprostheses, it's more of a problem. I mean, possibly the person can wear glasses and you can put things in or on the glasses, but even then having camera systems on the glasses can appear a little strange if people can see the glasses, so it's much more difficult. So here, issues with power, size, signal processing, but we're well down the line. Little bit of history because it's fun. Various scientists through history, all sorts of experimental scientists, and one in this field Volta, who the Volt's now, in the 1800s, he was pushing electrodes into his ears and sending electrical signals to what he described to create bubbling sensations. So, I mean, how we'd relate those, I don't know, it's difficult to know, but he described them, changed the different pulses and tried all sorts of different things. Really crazy guy, but perhaps that was where the foundation for cochlear implants came from. More recently, 1957, these are really, if you like, treated as the founders or the pioneers of the field. Giorno and Aries, putting electrodes into the auditory nerves and tried different pulse rates, so different frequencies if you like, and we're getting things like bap, bap, up, low. So the person who previously was deaf was reporting simple little, that could be described as words. So the basics, if you put electrical pulses into the auditory nerves so you can recreate particular sounds. Now, all the different types of hearing loss, which we'll have a look at, bone conduction devices, which is based on the, if you do that, you get different sounds, those sort of things. That's really how a bone conduction device works. It's sort of vibrating the bone that way and can work. The middle ear, if the problem is there, rather than in the cochlea, then you can just get an amplifier which amplifies the signal, affects the middle ear. Then there's cochlear implants. I'm not really going to say auditory brainstem implants. This is going right into where the auditory nerve goes into the brain. So it's another possibility. This is if the auditory nerves are destroyed, if that's the problem. So partly it's looking at where is the problem and then overcoming the problem technically. But the cochlea or the hair cells are perhaps the big problem. So the outer ear, the pinna, gathers the sound. This is what we've got here. Connected to the ear by this membrane system, so pressure waves are affecting the membrane in the middle ear. The air pressure is turned into fluid variations, and then in the inner ear, the cochlea, these fluid variations cause hair cells to move, and depending on which hair cells move, that's the signal that's sent into the brain. A microphone works in a very similar sort of way, pressure waves in there and converted to a change in electrical resistance. Typically, telephone would be carbon granules and things like that. But it's using the same sort of technique to get from a pressure wave, a mechanical signal, into electrical pulses of some kind. And in this case, this is interesting. The cochlea has 30,000 hair cells, and when Giorno and Ayres' work first came up, people said, oh, we're going to need 30,000 electrodes because there's 30,000 hair cells. Not the case at all, as we'll see. What happens in the cochlea? Well, hair cells contract with the fluid wave, the travelling wave, and they act then as amplifiers for inner hair cells. The inner ear is encoding frequencies relating to the fluid movements, and lower and higher frequencies affect different regions. The cochlea is like this sort of snail shell, so how far the hair cells are affected depends on the frequency of the signal. So the cochlea is acting like a spectrum analyzer, changing in response to different frequency signals, is affecting the electrical pulses that go into the brain. If you've just got moderate hearing loss, perhaps the hair cells, some of them are affected, dying off. It might be a hearing aid will work. Simply amplifying the signal overcomes the problem. But one problem, if you do amplify the signal, that can cause the problem to get worse over time. So just amplifying the signal. But if you have profound loss of the hair cells, it doesn't matter how much you amplify it, the signal doesn't go through and so on. So this is where the cochlear implants come in. You can alternatively directly stimulate the ganglion cells to bypass the hair cells and so on. Types, different type, depends where you are in the world and whatever, who you are. As noises and so on. 10% of the world has some sort of hearing loss. For a quarter of those, then standard hearing aid, just amplifying the signals is okay. Don't need anything more. And it fits behind the ear largely. So if you don't need to go in to the cochlea, then you don't have to. Some people, the conductive hearing loss where the pathway is impaired, so it might be just getting over that problem. And then getting into the nerve cells, this is where the cochlear implant comes into being. So you don't necessarily have to have a cochlear implant. If it can be done in an easier way, then so be it. Reasons for it can be due, for hearing loss, can be due to infection, can be bacteria or some viral thing, can be some antibiotics can kill off the hair cells. There's also genetic links. So if your parents lose their hearing earlier, then you're more likely and so on. Or even hair cells not being generated due to genetic reasons. Whether we like it or not, hair cell damage due to noise, chemical pollutants, smoking, trauma, aging, there we go, as we know all those sort of things. Again, that can affect whether you have a cochlear implant or whether it's treated in a different way. So any type of implant or what's being used need to understand where exactly is the problem and what caused the problem. And hence can be counteracted dependent on that. For cochlear implants, again, I'm going to pick out bits from this, so there's bits you can read through if you want, but talking in terms of stimulating the cultures, the neurons, and it's the same type of pulse for any neural stimulation, charge balance. Biphasic. Biphasic means it's positive, negative, or negative, positive. And what you're trying to do is so that no charge builds up. So you push in a positive current, you push in a negative current, and that way you don't get a build-up of charge. So that's exactly what the stimulation is for cochlear implants and so on. It's localized within the particular hair cells that you want, how the stimulation is and so on, and you can control it in different ways. Typical cochlear implant, which we'll see in a second, is a particular shape with electrodes and so on. But which ones of those electrodes are stimulated in which way, which need to be stimulated, depends on the person's hearing loss. And typically, once the implant has gone in, then the person will need to work with an assistant to help her to figure out which signals, which electrodes need to be chosen, where the amplification is required. So there's quite a tuning process once the implant is in position. And it does, as we'll see, depend on the brain to a certain extent as well. So stimulation can be encoded in different ways for loudness and pitch and different frequencies, dependent on how the problem is. So for a cochlear implant device, you've got a microphone, you've got an external sound processor, power supply, circuitry for transmitting, circuitry for receiving, and then an array of electrodes which are positioned in the cochlea, as we'll see. Typical, I mean the first cochlear implants used maybe 6 or 7 electrodes. Now remember, this is 30,000 hair cells we were looking at 6 or 7 electrodes seem to be okay to get reasonable for understanding voices and so on. Now, the upper limit is 31, but typical best products will maybe have 28, 29. So we're looking at only, say, 30 connections. You don't need 30,000. 30 will do. And this again is important for looking at other types of electrodes into the brain as well. So you have a pair of magnets on the surface, one on the surface, one under the skin, so it's just holding the thing together, one on the outside, one on the inside. Signal is encoded. A lot of the stuff is going on outside. The power pack typically is on the outside. Again, we'll have a look at that. And then signals are transmitted transcutaneously over the skin from the outside inside using radio signals. And then a little bit of electronics, the demodulator, which is implanted, changes the signals to say which ones of the electrodes are actually being stimulated to what amount for a different signal. Signal processing, different products do use different techniques. Sometimes the whole waveform is preserved and all of the electrodes receive the same waveform. Sometimes the electrodes, this electrode is dealing with certain frequencies, that electrode is dealing with other frequencies and so on. Just to remind you, the main, although our ears can actually hear from up to about 20 kilohertz, I think, in the perfect form. I mean, you youngsters, you're mostly 20 kilohertz. And as you get older, that reduces to maybe 12. I think my one ear is about 12 kilohertz now. So I can never hear what my wife's saying to me at particular times. But telephones operate over this 300 to 4 kilohertz, up to 4 kilohertz. So you find a telephone, you can't actually hear a lot of high frequency signals. Sometimes you whistle over the phone, the person can't hear it, because it's simply not transmitting those signals. So for speech signals, you only really need up to about 4 kilohertz. You don't need the higher frequencies at all. We see something like bird song, you wouldn't actually hear. You can have somebody talking to you on the telephone and they go, bird sing. You can't actually hear it on the other end of the telephone because the signals are just not being transmitted. So if somebody's saying, can you hear the birds singing outside? Well, no, I can't, but it's not your problem, it's the telephone that's the problem. So cochlea are placed with respect to ganglion cells. This intracochlear, we'll see this is the sort of coil-like thing, or like the snail shell. The aim for placement is for coding the frequencies in the different, in a particular type of multi-electrode array where the electrodes go in at different points of the cochlea. And you see a little silicone rubber. It is silicone, not silicon, quite a flexible rubber carrier that is put in. Electrodes are platinum. Platinum is a cool material as far as the body's concerned. It doesn't reject it or anything like that. It's quite happy with it. I've had platinum wires for some reason in my body for about 9 years now, no ill effects whatsoever. They pop up from time to time and push them back in. But the body doesn't bother, it's just floating around and coming to the surface occasionally. So I think a 9-year study is quite a reasonable thing. So platinum electrodes, the body. The further in is the insertion, the lower the frequency. How far they go in, there's still a sort of a limit, and hence some of the cochlear implants at very low frequencies, the person has difficulty picking up the signals. 30,000 branches of the auditory nerve, as said before, can be divided into frequency groups. A couple of the products, we'll see this nucleus one in a bit more detail in a second. Combi uses electrodes in pairs. Again, we're looking at something like 30 millimetres, so that's dispersing them over the whole extent almost of the cochlea, missing out particularly the low frequency. And this one uses 22. This is a very common commercial product using 22 electrodes. I think that distance works out to be pretty similar to the other distance. So there are a number of commercial products out there. Yeah, so now this is where I'm going to turn this round because there is sound on this. What it is she's a good friend actually, Nikki, who had these implanted. She now has 2 cochlear implants. She got to the stage of being profoundly deaf. She could hear reasonably well when she was a kid, but then the hearing went away, as she will describe. But you'll see the pictures, that there is sound, but I think the only way I've got the sound on here is just to, so I'll turn this round so you might be able to hear it a little bit better. Put that there. So again, here we go for... So, some of the things to pick up from that. So she had never heard bird song before, and when the signals first came in, her brain didn't know what to make of the signals. So she had to learn to recognise them. So, that's what's making the noise, and then she could understand it. So the plasticity of the brain to pick up on signals that it's never heard before and learn what they mean and so on. And these are important points. When we come on to the human enhancement section next time round, this clearly is, the fact that your brains and my brain have grown and developed in a certain way doesn't mean they have to stay like that. The possibility with enhancement is taking on new signals that they can learn and adapt to. and that's what we can see in that case. But the brain there, her brain had to relate the signals to something, had to understand what that was.
So that simulation of that electronic very voice, was that how she actually hears?
I don't. I think it's a good question. We don't really know. From talking to her, I think she said it was quite electronic or tinny to start with, but it then became normal.
Oh.
You know, so because she had hearing before to some extent, but it just deteriorated.
Because if it was really like that electronic, hearing all the time, it would drive you crazy.
No, I think in that case, she does have to go in, as she said, every 3 or 4 years she has to go in and they retune. So I think partly as the brain is changing and maybe some of the other hair cells are dying off, so they have to but that's no extra technical. She doesn't have to have the cochlea taken out. She's had the same implants for quite a few years now. She doesn't like me to say how many years, but probably about 15 years when she first had the things in. I think she did have an upgrade in one of them a few years ago because the technology had moved on and I felt it was a lot better. But don't think it was a problem. It was just a possible upgrade. Just a few thoughts, because I think that when you see what it actually means in practice, it's important to pick out some important things. The most common hearing loss is due to the hair cells going, and cochlear implants are increasing in use. They're being used by a lot of people. I think first of all, they didn't get used so much for older people because older people were going to die soon anyway, so what's the point of the experiment? But now older people are not dying so soon. They're living for longer, and even if you lose your hearing at age 60, you can, well, I'm going to live till I'm 90, so 30 years, it's well worth it. So a lot of older people are now going through it because of the transition it makes. And the product's improved. It's miniaturized, it's got better, the total implantation, it's become a very regular thing. It's not such a major operation. And the lifetime of what's actually implanted, the power packs and so on have improved. So I have to say here, now they're also talking about the possibility of restoring hair cells as an alternative genetic input. But it's more talking about it. I don't know that I've seen any practical. But as with a lot of these things, when we're looking at the organs last time, maybe there's a mixture for the future, sort of a genetic techno thing. Now I'm going to talk a little bit about visual neuroprostheses, but they are nowhere near as well developed as the cochlear implants. It's much more of a research thing. And we'll perhaps see some of the problems as much as anything else. Again, a little bit of history. One of the people I'm picking up on here for strange reasons is Giles Brindley. He conducted a whole series of experiments in the 1950s. Whether how successful they were, but it opened the field up. In the last 20 years, there's been a lot of, this is visual neuroprosthesis, a lot of research groups tackling the things. Some animal studies as proof of concept, but with visual it's very difficult. You know, how is it proof of concept? Because you can't ask a rat, okay, what are you looking at now? Well, you can ask the rat, but it's not going to say, oh yeah, I can see that's green or that's yellow, it can't tell you that. So it's down really, the proof is when it comes to humans. And there's still human studies are fairly limited. I'm going to gloss around, if you Google, you see a lot of work from a guy called William Dobell at the Dobell Institute. He now ended up working in Portugal for some strange reason. He was going into the brain stem, so missing out. Again, there's an element to this, where is the problem? Is the problem on the outside of the eye? Is it on the retina? Is it in the optic nerve? Where are the signals getting to as to what technology is used? Well, he's gone in with experiments into the brainstem. Still very limited positive results on that. The first generation, if you can call them that, are potentially black, white, yes, no, is something there, isn't it, for the profoundly blind, but it's mostly still certainly experimental at best, but a lot of speculation as to what will happen. When you see a result out there in the, we've got the problem sorted, we've got a new artificial retina, but a lot of it is it's MIT speak, which is, yes, we can do this, we can do that. It means they can't actually do it, but we can, meaning in the future, do something like that. You have to translate from the American. But I love this picture for a number of reasons. What this is the Ratio Club, which was, they called it a dining club, but I think it was more a group of guys having a drink and things like that. But there's a load of interesting people in it. This is Giles Brindley, who I talked about as being one of the founding people in this field. Giles Brindley, he did a lot of work in visual neuroprosthesis. The main thing when you read about him is something that you would never believe ever would happen. He's still alive, by the way. I mean, he's now Sir Giles Brindley. He's still a strange guy. But one of the things he felt was that in males, an erection can be brought about chemically. That was his thesis. Now, rather than just show, because if you have a problem, if you want to show it, here's chemical, here's the erection, yes, but you could have been reading a naughty magazine or watching a film at the time. So what he did, this is straight truth, various reports, the people there, he was at an academic meeting, and this is, full thing, and people found it a bit funny because he looked as though he was wearing some tracksuit bottoms. And he actually showed it, experiment. He dropped his tracksuit bottoms to show that he had this erection that was chemically brought about. And he invited people to touch it. There we go. I mean, it's fun to read the reports. People that were actually there, I can't believe it, but this was in about 1980, something like that, when he did that. But anyway, the reason I'm saying this, strange folk scientists are, but visual neuroprosthesis. The other pictures here, this is a guy, Ross Ashby, who was originally a psychiatrist, but he was one of the founding fathers of the cybernetics movement and so on. This guy you may have come across. Yeah. Go on, who is it then?
The guy who made the Turing test, right?
Alan Turing, yeah. I'm at Charles University, if anyone's interested, tomorrow afternoon, talking about the Turing test and things like that. It's one of my interests. So Alan Turing, pioneers in computing and so on and so forth. Various people. Horace Barlow, he's still around and he did some work in neuroprosthesis as well. But the other person from my perspective, and from at least one perspective here, this guy is John Westcott. He's still alive as well. He was my PhD supervisor.
Oh.
There we go. So, first of all, you guys now, if you didn't before, you know the link to somebody else. So you have a link to me, who has a link to Alan Turing. So you're only sort of 2 or 3 away from Alan Turing now. The other thing for John Westcott, which I find cool anyway, his supervisor's supervisor of his PhD was Norbert Wiener, and Norbert Wiener's supervisor was a guy called Immanuel Kant, and Immanuel Kant's PhD supervisor, there's links to, anyway, Da Vinci and all that sort of stuff. So anybody that's doing a PhD with me, when they get a PhD, we'll have links directly to Norbert Wiener and Da Vinci and Rene Descartes and people like that. So there's Giles Brindley, anyway, he was part of that sort of drinking group. General ideas here, again, it's the same sort of thing that we looked at in the audio. This case, video signals picked up by camera typically, processed before stimulating the neurons in some way. So you need some sort of external stimulator with electronics. Again, external. Now you have problems, because whereas with the cochlea you could put a lot of the power pack and all the processing behind the ear, which the ear is handily there, with visual, where the hell are you going to put it? You could start shoving it behind the ear instead, but then you've got wires and links and time to get signals and so on. Maybe you can put to some extent on glasses, which you'll see, but again, cameras are relatively big things and so on. So it starts to be a problem straight away. The other thing is, with any surgeon, it's preferable for the implant to be complete. What's happening with the cochlea is you've got a radio signal pushing, which you can do with auditory signals. With visual, how the hell are you going to get the signals in and not? And so what you'd like is for everything to be implanted rather than things to be... and implanting a camera is an issue. So there's problems with that. You need particular locations if it's going into the retina. And maybe each location is linked to each electrode, maybe you need more electrodes. So various devices are being prototyped, VLSI devices, but sealing, hermetic sealing to keep out infection and so on is difficult. Perhaps the most successful, again, different approaches dependent on where the problem is. The most successful, realistically, is perhaps the artificial retina, which is all about putting electrodes on the retinal surface and then stimulating them. So attaching electrodes to the inner retina, and then patterns of electrodes are stimulated to bring about different responses. You want the organisation to be as simple as possible. Questions though, can it be permanently attached? We don't know the answer to that at the moment. It's experimental, short-term periods and so on. Can useful signals be obtained at safe currents? We don't really. It's all very, very limited. Some of the problems, one is if you're putting everything, implanting it, where the hell do you put the power pack? So this is a little electrode array that's pushed onto part of the retina, but actually implanting the power pack in the eye, it sort of seems all weird. So it's more of a research thing at the present time. You can go into the optic nerve to bypass the retina. The optic nerve is just a single conduit. It's like a freeway, motorway into the brain. And you can, different researchers, cuff electrodes it's like a collar or cuff which clamps around a whole bunch of nerve fibres, and it has electrodes in it, either down or round at different points, and the electrodes can be stimulated. Again, it's biphasic pulses, and you're dealing with things like 350 microamps to get some sort of response. This is 350 microamps. It depends on the power, so it depends on the voltage as to what power is actually going in. 350 is getting quite a hefty current, I have to say. If I look at that, I sort of what I had in my nervous system for the experiments we did was about 80 microamps. I mean, I don't know whether you know about that research, and so I'm not going to go any more into it. We'll talk about it next time for the enhancement. But it's about 80 microamps. So 350 microamps to me, I was sort of a little bit like that. It's quite a hefty current. Stimulating 8 to 10 hertz. And basic research, people have been with a head-mounted camera, you know, out of 3 or 4 objects, being able to say, yeah, that's the ball, this is the brick. But very, simple. Yes, it's there. No, it's not. And so there's thoughts, rather than a spiral cone, of having a multi-electrode array of the spiky thing, so lots and lots of different electrodes going into the optic nerve. But the final word on the visual, because there's not a lot more to say on that. 4 possible sites. We've looked mainly, or talked mainly about the epiretinal, the artificial retina. This is the subretinal, which is the sort of next thing to wearing glasses, I guess. The optic nerve is another possibility. And then for visual cortex, have a look up on William Dobell, and that's the work that he's done there, brainstem. Passive photodiode arrays are no good. You can't really use passive devices. You need something that excites the retinal neurons, so you need power supplies and so on, which presents the problems that it's not so well conditioned, if you like. Stimulating electrodes need to be positioned. So this is the wires that are pushed in one way or another. Need to be positioned close to the neurons that they need to excite, and need to be of the same sort of dimensions. So you're talking a small number of micrometers. Maybe 2-3 micrometers for the electrodes in diameter, that sort of thing. And you need highly localized current injections with electrodes penetrated. And electrode arrays, such as the U-type array, are perhaps the best way ahead, but I'm not aware that it's actually been tried in this way at this time. And the first human trial for that electrode array that they're now talking of for artificial retinas was 2002. And you know very well the first person that tested it. So the final thing I'm going to look at in this one is the sort of things you can try yourself at home. So this is if you fancy experimenting a little bit. Partly because it's some of my own students, not here, but back in the UK, that are doing some of this stuff. So it's changing sensory signals in ways that you can do at home, I guess. This is Jawesh, who was a master's student with me. What he's receiving are magnets implanted in fingertips. So this is, again, the guy, out of interest, the guy that does it is not a doctor, he's a tattoo artist, and you can actually see some of the tattoos on his arm, which creates problems. We have to get ethical approval for doing this with the students. And the guy, the tattoo artist that does it, has the name Dr. Evil. You can't write this stuff, this is true, which creates problems in the university because it says who is carrying out the medical process, Dr. Evil. There we go. So you can see him putting the magnets in place, and 3 of my students have these things in place. Now you can see an X-ray of the magnets in the thing. So there's little permanent magnets. You notice it's the left hand because the student's right-handed typically. So here's Jawesh with what he's got are ultrasonic sensors on the baseball cap. For those of you who've done with robots, you've probably dealt with ultrasonic sensors. The output from the ultrasonic sensors is fed down to this coil of wire that is wrapped around his finger, in which is the magnet. So as something comes closer, the current in the coil changes and the magnet vibrates more. As something is further away, the magnet vibrates less. So it's altering the sensory input. Distance is converted to a feel, a touchy feel in the fingers.
May I ask, why do you stimulate the finger using the magnets inside and not use the electrical nerve stimulation of the fingertip itself?
Outside. It's much, much more sensitive to get a whole range. You can do it to an extent outside. We've done a comparison. One student last year just stuck magnets on the outside to get some sort of sensation. It was nowhere near as sensitive as inside. And it's, you know, you're going straight into a whole variety of different perception receptive nerve fibres, and picking up different frequencies that you just simply don't get on the outside. You're going straight into nerve fibres, really, straight onto them from the inside. And the sort of, you can get reasonable accuracy of response. Ian, who is another PhD student with me at the moment, he is feeding in infrared, which gives a sense that you can detect heat remotely, but also audio. So he's feeding in audio signals. I think they work, particularly the lower frequencies. You can get quite distinct differences. But we're trying to get into, can he listen to the first few bars of a particular Dvorak piece and just feel what the music is one of the things we're interested in looking at. Right, so is that next? Oh yeah, so we're going to have another 5 minutes and then I'm going to get into deep brain stimulation. Just to remind you though, the deep brain stimulation we're going to look at today is the basic techniques that are involved, and then we're going to look at the sort of weird and wonderful. We won't look at Parkinson's disease or epilepsy, we'll have a look at that next time, but we'll look at the other things that are being treated using deep brain stimulation. Okay, so take 5, get some coffee, whatever, and then we'll get on with this one. And then I plan to wrap up at 12 o'clock, so... Yes. Yes, the answer is yes. Very small. They are permanent, so very small. You know, pins. Yes, you can.